Hi everyone, my name's Thomas Kerin. Title of the talk today is Working on Scripts with Logical Opcodes. It's kind of going to be, I'll speak on it from the point of view of like a library maintainer, someone who tries to like, make it write code so that other people can sign and work with Bitcoin transactions. So working on the point of view of how do we work with these scripts, scripts that have logical opcodes in them. The talk will mostly go through a few things I worked out at one point, and just what I thought about it and what I'd like to see. Before I get there, I'd like to say thanks to the Speakers Committee and conference organizers for making it happen, and for letting me be here today. So Bitcoin has logical opcodes in them. We can use those to embed different redeem conditions for a Bitcoin. So depending on who's trying to spend the Bitcoins or what information they have, they interact with these logical opcodes so that to express all of those. So you can see a simple example here, taken from one of the Lightning scripts. It's really simple. So the final thing to so it uses if and else to push a different public key onto the stack, so later the check sig can run. So it just allows you to have a dynamic public key, and we can see it adds a relative time lock as well. So so two different people can interact with this script, and we can set different constraints on those being redeemed. So they can also get quite big. So if you're trying to write software that would interact with these, it can be a bit of a pain to sit through and work through on a case-by-case basis exactly how to interpret them, parse out signatures and stuff. But also when there's multiple branches in the script, the requirements differ from branch to branch. So mostly what this talk is about is just having software methods for splitting up a script into its separate branches. Let's see. So a quick intro on just how all this happens. So the logical opcodes control a Bitcoin script's execution flow by just managing a stack of booleans. Before every opcode is actually processed, we check if execution's active. So we can see it there, it counts false values in that stack. And before anything is actually done, we check if fexec is true, otherwise nothing happens. And that so if it's false, those opcodes are invalid and the conditional block isn't being run. So if and not if consume values from the main stack and push values into the VF stack. So they ultimately test some condition and consume a stack value and then put it into the VF stack, and that's going to change our flow control state. They work by like converting whatever stack value they found into a boolean and doing something with it in the case of not if, and then just pushing it onto the stack. And this is how and this interacts with that previous slide where we check and see if execution is actually active. So these are these opcodes are what we use to test some condition, and there's also else and if. So else just modifies the VF exec, so it can what it'll either do is just activate or deactivate execution. So if it wasn't executing, else might make that value true again, and then it would run. And if pops a value from the stack, so it'll pull you back out of the conditional section, and it just removes values from the VF exec. So traditional scripts, they don't have a lot of scripts don't make use of this. So fexec is always true, and they're always run, and they're pretty easy to. It's pretty easy to work out what. Sorry, my laptop's making a bit of noise there. And it's pretty easy to reason about what steps you got to do to actually sign them. So in the case of public key hash, you can just consider all the opcodes as one big template, and then you produce the signatures for, based off whatever pub key hash it indicates some key somewhere. So this is a script from I think it's one of the mass BIPs, BIP 114. It's just a hash time lock contract, but we can see there's three pathways there. So I just used T to sort of signify that the fexec was true and that the script, so yeah, there's 3 branches, and under each branch we have T for it was executing on that line, or just blank and it wasn't actually executing. So we can see that, yeah, under the 3 pathways, different parts are active. For example, Alice can only sign in the rightmost path there, and yeah, the 2 on the left actually allow Bob to sign. And below we can see, yeah, that different things are actually required in terms of the inputs in order to, yeah, cause the flow control to go to the right direction through the script, and yeah, what signatures would be required to satisfy what was necessary. So, and just to point out something, the values that just above each of the paths there, the 0s and 1s, those are whatever values would have been pushed by if and not if at the time that they were passed by, and eventually led to this code path being, and eventually, like, so these are the values that would, if and not if, would push into the VFXX stack, causing flow control to go in a certain direction. So they're unique. There's no duplicates there, and they all uniquely identify a different branch. Obviously, if it's executing, there won't be false values in the stack, but it's just, again, it's to point out that if you wanted to go into the second branch, the first if would push a false value, else is going to convert that into a true, so the execution will be active again. And yeah, so that's why the 0s and 1s are there. So to actually identify the contents of the branch, or supposing we have some software that can support signing any script, including these kinds, so we'd probably need to be able to identify the branch to them so that it can also take that branch in isolation, see what the signing requirements are. So to do this, we can just iterate over the script's instructions and partially interpret them. We only really need to look at the logical opcodes, track some state about those, and and then whenever we encounter an if or not if, we now know that we have a new conditional block or a separate code path that we have to consider. So every time we have an if and not if, we end up with some more code paths because there's a new conditional section. Opcodes may or may not be associated with that, and yeah, pretty much we just proceed over the whole script. We associate all the opcodes with each part, with each code path, and yeah. So since it's a general method as well, we want to like check that unbalanced, or check for invalid scripts. So if any, if any code path while we're tracking the changes to the VFXec, if by the end of the script it still has contents in the VFXec, it's obviously invalid. It wasn't fully balanced. So yeah, we can reject those. And I have a really like nasty slide on, I guess, just what it's doing, and yeah, and at what point information is known. But I think it's sort of mostly explainable here. So we can see at the start there's a box with nothing in it, and this sort of represents the start of the script's execution. There's been no logical opcodes yet. So this hash lock part of the script, every code path is going to include that. So then we run into the op if. We know there's some conditional section. It would need true to actually enter this part. So we see that that's on its own. There's no further nesting in that in the branch where it was 1. So it doesn't go any further. We then see that the else opcode indicates that okay, there's a case where it could have been 0 or false. We also see that there's further conditionals nested inside that. So yeah, and they're actually the same values that we wound up for, yeah, as naming our code paths earlier. So you don't need an else either. So So yeah, we saw there was an if-else in the lowermost conditional block, but obviously the innermost not if, it may or may not actually enter that, so that's why it also gives it a 0 or a 1. You don't need an else. So after going through all this, you step over each instruction. You look at after each. Yeah, and during each opcode, you look at which code paths are currently active. So yeah, since you're tracking the VF-exec for each code path that you are building up, you're able to see exactly which code paths are active at which time, and therefore you know which code paths to assign the current instruction to. So yeah, I'll just skip that. But so now we can actually see just the. Yeah, we'll have a look at the code paths now that we've pruned away all the unnecessary instructions or the stuff that's irrelevant for the path we want to assign. So here's the first path where Alice can provide her signature. Yeah, we can see it's just now there's a hash lock she has to satisfy, there's a relative time lock, and then she can provide a signature. And the next path, Bob's allowed to spend without knowing the pre-image for the revoke hash, but only after some date. So we see that in that case, the not if is the second conditional we run into. It's currently 1, so that means that he did the equal tested false. So yeah, for the software, it's able to say, okay, I don't need to know either of these hash locks in order to go into this section and for him to redeem this way. So if he enters this branch, he just has to wait until some date passes and then he can sign. Or if he knows the pre-image, he can sign and redeem it at any time. And yeah, he would have to know, satisfy this one, of course, not this one. And yeah, he doesn't have to know this one. So obviously, like, it's easier to start classifying the individual sign steps once you've broken it down into the exclusive code paths. So let's see. Yeah. So it's worth pointing out maybe that, like, I mean, even stuff like a LND or things that are actually using these don't really need to undergo this treatment, because usually it's just it's small application specific and you can just put together the primitives so that it all works out. But what kind of interested me was having some sort of general method and being able to take arbitrary scripts which might compose smaller script snippets and ultimately be able to make software be able to reason about those and sign those. So let's see, I'm just gonna switch out. Sorry, this is somewhere else. Oh. Yeah, so this is actually from BIP 1112. I think it's just an example of using check sequence verify, but it can be a multisig in the first branch, and then the second branch it uses a relative time lock, and then a signature can happen. So we can split out so here's the second code path, the case with the time lock and the signature. So after we've learned what opcodes are in that branch, we can now split up and actually see what the operations we'd have to satisfy are in this case. So we'd see that there's some conditional if, and we'd need to make sure the flow control was, or the value push into VF-exec was false, so that we get the intended outcome of flow control. Next is check sequence verify, which yeah, the software parsing could tell what the TX input sequence needed to be, and then yeah, which public key. So yeah, this is some software I'd written, but obviously it's on a PDF. I just wanted to make sure it would work on the day. But yeah, so it can, so yeah, and yeah, it's able to put together the witness structure. We can see the second value down in the witness section is that false that we needed in order to trigger the right flow control. And yeah, that last thing is just the witness script. So, and of course as well, just point out the talk isn't so much about like what you can support in the signing operations. Yeah, more about just the branch parsing. We can see the other branch then. Yeah, it's just a multi-sig, not much going on there. And yeah, just it can, again, fill out the stack so that it actually ends up in the right place. Sorry, that's all we had there. Okay. So the thing that actually got me to consider this problem, or just to look at this in the first place, was looking at some of the mass BIPs. I think it was so Merkleized abstract syntax tree allows you to take like these large scripts with multiple redeem conditions and then flatten them out so that when you're redeeming one, the details of the other scripts remain private. So there's currently 2 proposals to add mass to Bitcoin. What I found interesting about it was that if you were to take a legacy script and then to try and convert that into its mass equivalence, yeah, that was initially what kind of got me started onto this problem, and I have to say it was something I never really fully cracked either. It did make me look at the whole problem of solving for mutually exclusive opcodes in each pathway and everything, but there's more side effects that you need to look at in order to properly flatten down the script. So here's the script from from Johnson Lau's BIP, and yeah, it's really interesting because you can see even down at the top is the full script, the bottom is its masked equivalent flattened branches, and we can see that there's really, unlike the earlier ones when we weren't trying to eliminate the logical opcodes, we really see differences compared to the original script and the flattened ones. For example, the dupe opcode was completely removed because the only reason you need that there is when there's multiple possible branches that could be encountered and you just need to manage the stack so that later, if it happens, the right value is there. So that one completely gets removed. You can also look at stack side effect or instructions that are only relevant in certain branches. So yeah, you can look and see that, like, if the dupe is removed, well, then the 2-drop won't need to be there. So generalizing this and getting into software, I think, is harder, or something I haven't quite gotten yet. And also you need to look. We see in the last one there isn't any signs of hash locks at all, even though those were the cases where Bob didn't know the first hash lock or the second hash lock. So we need to look and see, like, okay, was this instruction actually required in the outcome of the script? And if not, we can just discard it. But yeah, generally that was the problem I wanted to tackle. I found it really interesting, and just there was a lot going on just to take from the top half to the bottom half. So mass isn't really on the network today either, but I did find it useful because, again, from a library maintaining point of view, I could take the mutually exclusive opcode parsing stuff, and if you want to work with logical opcodes then and sign a particular branch, well, then the software could do that, and it could actually make sure that you weren't, say, signing the wrong branch or revealing the wrong pre-image or whatever. But I think, I think I've only gotten as far as the first one. But so to massify a script, or to take a large one and convert it to its mass branches, you need to determine the mutually exclusive code paths of the script. You need to, so any logical operators, which are just tests for flow control purposes, can be replaced with assertions about the state of the stack. So you'd replace if with verify, because it would verify that the value cast is some truish. Not verify for not if. Oh, this laptop's touchscreen. Also, you can further tweak things by you might see a check sig beside a verify now, because it was like check sig and then op if. So those can be merged together, so into op check sig verify and stuff, so you don't have 2 opcodes and run into the opcode limit. And then, yeah, the big one was trimming instructions used by the old script just purely for flow control purposes, which are totally unnecessary in the mastified branch. And I think that's it. So there's some projects that have some of this on the go already. I maintain Bitcoin PHP. It has, this branch parsing stuff, but nothing masked yet. B2C Deb, I've been looking at it a bit too. It's Cali Wolf's project. It has the whole like mastifying, but without like trying to remove unnecessary instructions. So I think if you were to give it this script, it would leave all the hash locks in and so on, which is still acceptable, but it's just it would have a negative effect on the witness size and transaction fees. And then, as far as I'm aware, Nicholas Dorier also had something as well for mastifying. I think it had similar issues, all right. It just needs as well to be able to remove hash locks or unnecessary instructions. But that's it. Any questions?
Thank you for this very good presentation. Can you tell me where you try out the scripts that you built? Is there a tool that you regularly use to verify them?
You can use B2C Deb, or Bitcoin PHP is some stuff as well. Or if I actually sign something, I would run it through libbitcoin consensus because I have bindings to that in a few languages as well. So I can actually use Core's verify script function to check that when I did sign it, it was correct, and yeah.
Hey, Bitcoin Cash recently reactivated a couple of opcodes. I was wondering, since you are deeply involved in the scripting with the opcodes, what's your opinion about re-enabling old opcodes?
I'm not sure the implementations were necessarily the same. I mean, they're just going to hard fork anyway, so I mean, it's not as if adding new opcodes back is going to be an issue. I know there are, like, some of them would have been removed, I guess, because of concerns about like memory consumption, or just, they weren't written correctly or safely at the time. I hope they fix that. But I don't have major thoughts on just what it means to take them out and add them back. You'd hope they're okay now. Great, cool, thanks a lot.